And now we move into the next journey in statistics. We saw simple linear regression, 1x, 1y. Surely we felt deep inside that there was more. There was more we could do with this. Oh, so much potential. And now let's realize some of that potential by moving into the more realistic type of regression, multiple linear regression. Okay, so in this unit, we'll do the model, very similar to what we saw in simple linear regression. Estimates, of course, of the coefficients, very important. Again, we saw that in simple linear regression. So the assumptions stay the same. We use the methods of least squares, so that's a commonality. Coefficient of determination, similar interpretations, slightly different in calculation, and the all-important interpretation of results. Because, of course, we are in an applied field, in an applied degree program. Therefore, applications are extremely important to us. Okay, so when we were restricted, I hate being restricted. It's sort of like being quarantined in your own house, right? We urge to live free. And so when we only have one predictor, right, and we know there are other predictors out there, right, and other x variables out there. Wow. Where's their effect felt, right? I mean, if they exist, that means they're being influenced. The fact that whether we can see it or not is irrelevant, right? Their influence is felt. And where is their influence felt? And that is in the error term. Okay, so any variables that should be in the model that aren't in the model show up in error. Now, we saw when we first talked about error in simple linear regression, some of those errors may not be quantifiable or easy to bring in to the model. But where we can, we want to bring them into the model. Okay. We use the F-test for model significance in simple linear regression. We use the F-test here as well in multiple linear regression. Awesome, right? We use the t-test to test an individual specifically named variable. We do the same thing for multiple linear regression. Okay? So we use the F-test and the t-test the same. We will use the R-squared to check for goodness of fit, but we're going to make a little bit of an adjustment because by adding variables, you can kind of cheat a little bit on that R-squared, make it increase when by adding variables that, basically are full of crap, okay? So we want to sort of avoid doing that. So we got a little bit of an adjustment that we'll make to R-squared. Other than that, interpretation, it's the same. Okay, so I know, going to go through the slides, and I've done this before, and the slides are wordy, and they violate PowerPoint rules all over the place. But we want to get some realistic examples, and you could read this. I'm going to say it a little bit. Okay. Increased employee retention. One of the things that we can use regression for is to predict whether an employee, or how long an employee can be expected to stay with our particular company. Okay. We can do a different type of regression, which we won't do in 312, where we can say, will an employee be promoted, not be promoted, and those kinds of yes and no's kinds of questions. We can do regression for that. It just wouldn't be the regression that we talked about. It would be a different kind of regression. It's called the discrete choice modeling, and there you're in the realm of things like what's called a probit model or a logit model. Okay? But there's still types of regression. But let's say we want to see, okay, how long an employee can be expected to stay with the company, given a variety of parameters. It's very expensive, especially the higher up, the more skilled the employee, the more expensive it is to recruit, hire, and train them for the specific job. And once you've done all that and expended all that kind of money, you want an employee who's going to stick around for a little while so you can make that money back and then some, right? And you want that employee to be its own profit, or his or it, that's very bad, eh? His or her or their own profit center. And so we look at a variety of factors to see what determines a successful employee. And Google does this in a big way, and as do a lot of other companies. And ironically enough, it's not necessarily the super high GPA that's a high indicator of success in all particular firm. I mean, it really depends on that particular firm. So we can do all sorts of analytics looking at attributes related to employees, both ones that left very early or prematurely, and ones that we were able to retain for a significant period of time, and then see, okay, how important certain factors are to employees staying or employee longevity. So regression can be very useful in this particular regard. We could also look at factors that are negatively related to retention, right? Remember when we were talking about interpreting coefficients in simple linear regression, we weren't all just interested in things that were positively related. We were also interested in things that were negatively related. When we talked about sales in simple linear regression, it was very important to us to do the good things, the things that increase sales. But it was also very important to us to not do the things that decrease sales. So we keep both factors in mind, and regression allows us to have both of those factors brought into the model. Things that we should do, things that we should avoid doing. Another thing you'll see is customer profitability, right? What type of customer do we want to attract? In economics, we have what's called a Pareto distribution, and you see it in supply chain as well. And then that is where 80% of your sales are driven by 20% of your customers. You could also flip that around and say 80% of your problems are driven by 20% of your customers as well. And that power rule, we call it a power distribution, sometimes it's called a Pareto distribution, holds for a wide variety of factors. So income, for instance, wealth follows a Pareto distribution or a power distribution. And so we want to make sure that we retain the customers that are contributing to profitability, and then maybe sort of pushing aside or not focusing so much, or maybe even avoiding customers that aren't contributing to that profitability, right? If 80% of your profits are driven by 20% of your customers, then you want to know or be able to identify who those 20% are. Now, I know you could look at the sales sheets and you could say, okay, well, ABC company spent so much with us, and just rank them that way. And that's one way to do it. But you also want to look at it maybe from a longer term, and you want to look at it from the lens of prospective customers, right? So if you know who or the attributes related to your 20% of your customers that are driving 80% of your sales, and you're now evaluating how hard or how much company effort you should put into I don't want to say selling, because selling is, someone my age, selling is not a bad thing, and sometimes modern, aggressive sales has gotten a negative connotation. But when you're thinking of approaching a company and you're trying to establish a business relationship with them, you want to be establishing business relations with a company that has more of the factors related to those 20% of the businesses that are driving 80% of your sales than the 20% of the businesses that are driving 80% of your problems, right? So you want to be recruiting the former, or you're not recruiting, but you want to be pursuing the former, not the latter. And so you need to know what attributes are related to those attractive customers, so that you can then look into the marketplace and say, hey, here's XYZ company. They share many of the attributes of our great customers. Let's go approach them, right? Let's expend some company effort on them. And then somebody comes at you and say, well, there's MNO company, and then they look at their attributes, and you go, well, I mean, maybe we might pursue them someday, but they seem to not have many of the positive attributes we prefer, and so we're going to focus some effort on XYZ company first, then we can worry about MNO company later, right? So it allows us to prioritize who we pursue or who we expend company effort on. So that's extremely important, right? Because if you're talking about high-performing sales people who maybe have technical skills or now often have technical skills, we want to make sure that we're allocating them as a resource in the most efficient way possible. You'll also see a little bit of this in finance, a lot of this in finance, in that when mortgage companies extend a mortgage, they don't really actually want you to cash it in early, right? They don't want you to pay early. And so sometimes there's analysis that goes on into modeling customers who are likely to pay their mortgage early. They want you to pay the mortgage, don't get me wrong. It's just a matter of they don't want you to pay it like early, okay? Because they've sort of loaned that money out. They prefer to match it for a longer time period so that they can then be able to predict their cash flows. One of the big bugaboos in finance is, predicting cash flows and making sure that your cash flows are somewhat consistent. Because, of course, when you pay early, they then have the company, the mortgage company, bank, whatever, has to then find another use or purpose for that money, which, of course, has a front end or a cost at the beginning of that process. You have to find another borrower who fulfills their requirements. So it can be expensive. It's like almost like recruiting an employee is to finding someone to lend money to who will pay you back. It's easy to find somebody to lend money to, but you also want them to pay you back in the interest. Okay, so sometimes that can be that's the tricky part. Amazon has started to do this as well, is look at which customers are a real royal pain in the butt and kick them off. Right? And been a few surprised people, who, let's say, buy something and return it, buy something, return it, that kind of Yahoo. And Amazon has now started saying, okay, no, you're out. Boom, buzz off, get lost, beat it. And these people are like shocked, thinking, what do you mean? You're a very unprofitable customer. We don't want you. Get lost. Okay. And another way that we can use this is product shelf. Okay. So grocery stores have really turned this into we're the first to turn this into a real science with slotting, what they call slotting, and they'll allocate product in a very, very objective, data-driven way. Sometimes the data-driven way is you pay for a certain slot. So if you want a certain shelf space in a certain location, then you negotiate that with the grocery store, which may involve discounting or rebates or what have you. And so they look at that from a very data-driven, scientific point of view. And of course, there's certain parts on the shelf, certain parts in the store that are more lucrative than others. End of the aisles, very lucrative because everybody sees it, close to the cash registers. Very important because everybody sees it. Eye level, roughly at eye level on the shelves, that's very lucrative. Up high, not so much. Down low, not as bad as up high, but not that great either. And so on. People do tend to look at eye level and down. They don't look at above eye level. It's just a human trend. So if you're like at the top of the shelf, it's kind of an unattractive spot to be. You're kind of eye level and maybe, stomach level, like in that zone, that's the sweet spot. So you will tend to see either higher margin goods in that zone or, it'll be higher margin goods, not necessarily higher priced, higher margins, which it just means that the grocery store is making more money on those particular products. So there's a lot of ways that we can use predictive analytics, of which regression is a part of, to make very, very important, very, very real life business decisions. Okay, now we can think of anything. So there were some things, and that's a pretty broad scope that we've already talked about, but we can think of anything. And if you could brainstorm and just think of something you'd be interested in. And usually in-person classes, when we do this, we've talked about coil notebooks and factors driving coil notebooks. In fact, in winter of 2020, we did makeup. I know nothing about makeup. I don't wear makeup. I basically wash my hair, comb, and go, right? So very low maintenance, and I'm ugly as a result. So we talked about maintenance, so makeup and all the attributes, and this I never knew, right? It was a very big learning experience, thinking of all the factors that go into what drives that sale, and influencers and all this kind of stuff, and various lines, and holy cow, right? So you can go through all that, and you can do that to predict such a wide variety of things. And then you think of the factors that are driving that, right? And then you'll run the model to see, okay, how do those factors, by how much do those factors on average drive sales for that particular product, or years of retention for the employee. So a very, very powerful tool, this multiple linear regression. Okay. So our objectives here, as we start with every unit, we'll define certain terms and notations, right? The models, the equations, and stuff like that, just so we can sort of get the beginning parts of what's going on. Okay. We'll talk about goodness of fit, just like we've done before. We have our two basic deliverables in that particular section. We have standard error of the estimate, explained the same as before. We have an adjusted R squared, which is interpreted the same as the regular R squared. It's just adjusted for adding extraneous or not meaningful variables. We have some assumptions that we'll reiterate, because those assumptions are extremely important. I know assumptions have sort of a theoretical feel to it, and they sort of just instinctively turn your eyeballs up and back into the back of your head as you go, assumptions, theory, but not theory. Okay, they're important because we need to know if our model isn't accurate, or isn't robust, or isn't doing what we think it's doing. We need to know that. And if assumptions are not being followed, that means that model is not predicting what we think that model is predicting, which can lead to some very expensive mistakes. And then we'll talk a little bit about Excel, and we'll always be interpreting that Excel output. So just like we did with simple linear regression. Okay, so the model, and I know when we talked about models with simple linear regression, model essentially meant we had an error term. Okay, so we see epsilon in the population model. We see E in the sample model. E just means there's a specific value for that E. Okay? And we have our parameters, and we have our independent variables. And when it's a population model or a population, the line, we have Greek letters that represent the coefficients, because we don't know what they are. They exist, but we don't know for sure what they are. Right? And they exist across the entire population. Well, we can't survey, as we know from our very early stats experience, we can't survey everybody. Way too expensive, takes way too much time, and so we can't do that. So we take a sample, and we make estimates based on that sample. And the idea is, if we've taken proper estimates, we've taken a proper sample, that those estimates should be a reasonable representation of the population model. Little bit of standard deviation to every one of those B's, every one of those coefficient estimates, because maybe our sample was a little bit wonky, right? That happens, but we can measure that, and we can move forward from that and see whether that's sufficient or not. Okay. And then we have the equations. Right? We have a population regression equation. We have a sample regression equation. And just like with the simple linear regression case, They're either expected values, which is like another word for saying averages, or they got the little y hat, which again is just another way of saying average. Okay? We have our regression coefficients. We don't know what they are in the population case, so they're represented by the respective betas. We just have more of them, right? Goes up to beta p. That just means however many there are. P being the number of parameters. P for parameter, by the way. Okay, and same thing with the estimates. The expected value for the errors is 0, right? Just by the nature of the least squares regression method, the expected value of the errors is 0. So when we deal with expected values, or AKA the equation, we don't, the line has no fluctuation, so there's no error. Okay. If you like fancy language, we have p parameters, and so when you include the intercept, we have a surface essentially in p plus 1 dimensional space. It really doesn't have a practical meaning, but I think it sounds just so damn cool. Ooh, you know, that looks like a surface in p plus 1 dimensional space. And everybody looks at you like you've said something. Whoa, that guy is so smart. Not really, it's just fancy language, meaning representing a simple thing. Okay, so when we come back, next segment, let's do an example.